Every day you use image generation models, ChatGPT or Nano Banana by Google. It feels like you type words and AI paints reality. It feels like magic. But today, we won't just use it. Today, we will understand it from start to end. And since AI is the most demanded skill for 2026 jobs, especially in MAANG, we will also decode real interview questions on this trending topic. This is the system design of text to image. Explained the right way. For years, GANs ruled image generation. The system had two neural networks: the generator, the forger; the discriminator, the detective. The forger makes fake images. The detective shouts, "Fake!" They trained by competing, improving each other. It worked, but it was unstable. Sometimes the AI learned one trick that fooled the detective and then repeated the same image forever. That failure mode is called mode collapse. Training a GAN was like balancing a pencil on its tip. Engineers needed stability. We needed a system that learns to reverse a process, not fight it. And that shift was diffusion. Think of ink falling in water. It spreads until the glass becomes random gray. That is diffusion. That is entropy. Now imagine reversing it mathematically, starting from gray water and reconstructing the ink drop. That intuition became the core of generative AI. So instead of two models fighting, we train one model to answer a simple question. What noise was added here? We take real images and slowly destroy them by adding Gaussian noise, step by step, until they become pure static. Then the model learns to predict the noise so we can subtract it and recover the image. If you can recover an image from pure noise, you can also generate an image from pure noise. But one big challenge remained. How do we control what image comes out of the noise? That required the language vision bridge, clip, and embeddings. A modern text-to-image system isn't one model. It's a pipeline of three major systems working together. Text encoder, clip-T5, converts words into math vectors. Diffusion model, UNet and a transformer, sculpts meaning out of noise in latent space. VAE decoder converts the final math back into pixels. Let's trace your prompt. You type, "An astronaut riding a horse." Step 1, text to math. The computer doesn't know what astronaut means. So the text encoder converts words into embeddings, number vectors, where related concepts stay mathematically close. This becomes the guide for generation. Step 2, we compress reality. Pixels are expensive. A 24-ounce sonotutibor image has over 1 million pixels. Denoising that many pixels at every step would melt your GPU VRAM. So we use a VAE autoencoder to compress the image into a small latent representation, like a neural zip file that keeps concepts, not pixels. All generation happens in latent space. Step 3, denoise towards meaning. We start with pure noise in latent space. The text embeddings enter the model through cross-attention arrows. Inside, the model keeps asking, "This looks like static." But the user wants an astronaut. How do I shift the noise to look less like non-astronaut noise? And it does it step by step, 20-50 iterations. Every step removes a little bit of anti-astronaut noise. When it draws the helmet, it attends to the word astronaut. When it draws legs, it attends to horse. That is cross-attention in action. Step 4, latent to pixels. The final result is still compressed math. The VAE decoder inflates it back into high-resolution pixels. And you see the final image. This is why the system is stable, efficient, and controllable. Part 4, control systems. Directed design, not slot machines. Early diffusion models were random, like slot machines. You pulled the lever and hoped for the best. Today we have ControlNet, injects pose, structure, edges. And LoRAs inject style, face, domain tweaks. Now you can say, keep this face, change lighting. Use this exact pose, follow these edges. We move from random generation, directed design. Part V, the future, speed, control, and video. Diffusion is now evolving into transformers for better scaling across aspect ratios and resolutions. And video generation extends diffusion into the time dimension. The core challenge there is temporal consistency, making sure the astronaut doesn't turn into a bear between frames. The modern solution is treating video as a single 3D data volume and denoising space plus time together. Part 6, MAANG 2026 interview questions. Now let's connect this to jobs. Why not generate in pixel space? Because latent space compresses features and reduces VRAM plus compute load. How does text control the image? Through cross-attention, aligning specific visual regions with text tokens. What killed GANs? Training instability plus mode collapse solved by noise prediction in diffusion. How to extend a video? Treat video as a 3D volume, denoising time plus space jointly for consistency. These are the fundamentals interviewers expect you to know. Recap, quick rewind. GANs fought, diffusion learned to undo noise. Modern text-to-image is a 3-model pipeline. Text, embeddings, images, latent space. Latent noise, denoise towards meaning, latent pixels. Elegant system, simple intuition, big impact. So we began with everyday you use image generation models. And now you know why it actually works. It's not magic. It's system design that reverses chaos, guided by language, powered by math, optimized by compression. And this is why AI engineering will dominate MAANG hiring in 2026. Keep learning, keep designing. Don't forget to keep learning, keep designing. Don't forget to like and subscribe. Thanks for watching.